Okay, Physics 111. Now we're going to talk about multiplying vectors. Okay, so we might multiply a vector times a scalar. So the very first thing is what happens when you multiply a vector times a scalar? Well, a vector times a scalar is actually pretty simple. So we've already done this. We just didn't say it was multiplying a vector times a scalar. But when we multiply velocity, which is a vector, times time, which is a scalar, then we're getting a displacement, right? This becomes displacement. We had one-dimensional motion where we had v times time and we had sort of a delta x or a delta y, but it's a displacement and we'd say delta r in 2 or 3 dimensions instead of delta x or delta y. I hope that makes sense. So if we do that, say our velocity actually, and we wrote, this is written in unit vector notation where I have, okay, in the x direction, the velocity is 5 meters per second, and in the y direction, the velocity is 6 meters per second. So if I multiply that and I say, well, let's assume that we're talking about 10 seconds. If I multiply these together, I multiply 10 seconds times the 5 meters per second and get 50 meters, and the 10 seconds times the 6 meters per second and get 60 meters. And so my displacement, again, in unit vector notation, is 50 meters in the x direction and 60 meters in the y direction. And so I end up with another vector. When I multiply a vector times a scalar, I end up with a no vector. It's in the same direction as my original vector, unless I've multiplied it times a negative, a scalar. I guess it's in the same parallel direction. If my scalar was negative somehow, if I said negative 10 seconds in this situation, then I would be in the opposite direction. But it's parallel, let's say that. It's parallel. Is parallel to the original direction. To the original vector. And so that's really straightforward. Now when you multiply two vectors, there are two different products. There's two different ways of multiplying them, and they're not the same. You don't get the same thing out of them at all. They're actually two different products. It's like, do you want product 1 or you want product 2? But we don't call them that. One is called the scalar product, or more physicists are more likely to call this the dot product. The scalar product produces a scalar. It does not produce a vector. You take two vectors, and instead of getting a vector out, you get a scalar out. Something that does not have a direction. It only has a magnitude. And what this scalar product is really concerned with, what it's asking when it does the product, is it says how much of these vectors, of these two vectors, are parallel to each other. It's only going to multiply the components that are parallel to each other. The parts of those vectors which are perpendicular to each other, it will not multiply. It'll say, so if you had two vectors that were perpendicular to each other, so you had a vector and b vector here, and they were perpendicular to each other, the scalar product of this would be 0. No parts of these vectors are parallel to each other, and so the scalar product would be 0 for this. It's only when there's some parts of the vectors which are parallel to each other that you get a scalar or a dot product. Now the other one is the vector product. The vector product, or is often called the cross product, it has to do with the way we write the mathematical functions between them, that we say cross product and dot product. The vector product produces a vector. Is Captain Obvious moments here. And what this vector product cares about is the exact opposite. It wants to know how much, it's looking to multiply the vectors, the amount of the vectors which are perpendicular to each other. So if the vectors are parallel to each other, say you had a vector and b vector, the vector product of these two would be 0. Right? It only cares about the parts of the vectors which are perpendicular to each other. Let me tell you, go ahead and just talk about this thing. So the scalar product, one of the things that we'll use this semester that we talk about that's a scalar product is the physical quantity called work. And that's when you have a force acting on some object. So say I have some box here, and that force makes the box go some displacement this way. We'll write it that way, right? It has some displacement. The work is going to be the dot product between the force and the displacement, because the force is actually making it do that work. But say my force is actually not in that. So say I have some force which is actually pushing up like this. We might have a normal force on it. In this case, the normal force does no work, right? The two forces, the two vectors here are perpendicular to each other. The dot product is 0, and that's true. That force, if it's pushing up, it's not causing that displacement. Why it's displacing wouldn't be because of the normal force, but it's not. The normal force isn't doing any work, and so the force, the work done by that normal force would be 0. I'm going to erase that because that looks really confusing. Probably. Well, maybe not. We'll put it back. Another thing, so this is what we call work. For vector product, we have a thing called, a physical quantity called torque. And this is if you want to open a door. You do torque. So if this is my door from above and this is my hinge. A torque is basically something that makes it move around. It causes some object to have some sort of angular motion. And so that's what happens when you push on a door, right? In this case, I'm going to have some force. So say I push here with some force, which is a vector. And then there's what we call the lever arm, or the distance to the axis. Here's another, so we'll call that just R. If these two are perpendicular to each other, I get the most torque. I get the biggest amount of torque. If instead of that force being perpendicular, say I did it this way, instead say I pushed like that with my force, then I wouldn't get as much torque, right? The door wouldn't open as easily. So torque is the universe's way of doing a vector product. Work is one of the things we use for this dot product. I'll leave the other one, I'll put that one instead. So in this case, torque and work are just physical examples of scalar and vector products that we'll do later in the semester. So I'm going to do both of these with some example vectors. So I'm going to have vector A be my first vector, written in unit vector notation. It's 5. I'm not going to put units here. We're going to live without units in this example. So 5i hat plus 6j hat. If I went through and I get the magnitude by using Pythagoras, so 5 squared plus 6 squared takes the square root, that's 7.81. And that has an angle of 50.2 degrees like this. So here's the positive x direction right there. And then for my b vector, I'm going to have 3i hat minus 10j hat. So it's down here. So it has an angle of negative 73.3 degrees. Here I've gone clockwise. So I'm going to give a negative angle and a magnitude of 10.4. Yeah, so those are just going to be my example vectors that I'm going to use when I do these calculations. So let's do a scalar product first. And again, this is an example of that, is work done by a force. So you get a scalar out of it. So I'm writing little c is my scalar. And these are equivalent. So A dot B. And so for a dot product, we actually write A, and then we write a little dot, and then we show the B. So the dot part of it is this. And so then we take, you can do it 2 ways. You can do the magnitude of A times the magnitude of B times the cosine of the angle from A to B. Or if you knew things in unit vector notation, you can say A dot B is AX plus times BX plus AY times BY, and then AZ times BZ if you had it. And that's because I dot I is 1, J dot J is 1, and K dot K hat is 1. All the other ones are going to be equal to 0 because they're not parallel to each other. Remember, the dot product wants to know how much is parallel between these two vectors. So let's look at these different situations. So did I do them? I didn't do it. Okay, let's do the math. So if we do our situation here, so I had A dot B, and if I do it where I know the magnitudes and the angles, so my magnitude of A is 7.81, and my magnitude of B is 10.4. And then the cosine of the angle between them. So here's B and here's A. Let me redraw those. I'm going to draw them in the same coordinate plane. So I have A here, right? And this angle, I'm sorry that I keep going back, is 50.2. And then B is down here, and this is 73.3. And so the angle is the sum, right? The angle between them from A to B, or the angle between them, is the sum of those. And so if we go through and do that math. All right, so I get a negative 44.8. And that's okay. There's not any units for this. Our physical example was work. Work can be negative. You can have a force which goes the opposite. Anyways, don't freak out on me. A scalar can be negative. Time can be negative. It just means that it's sort of, it'll be, depending upon the physical quantity, it tells us different things. So that's what we get if we use the magnitudes and directions to do our calculations. If I then instead do the other way, I say AX plus BX, AX times BX plus AY plus BY, what do I get then? So here we go again. I have 5 and 3 and 6 and negative 10. So I say 5 times 3 plus 6 times negative 10. So this is 15 minus 60, and I get negative 45, which this should also be negative 45 to my two significant figures that I had. And so I get the same answer from the two different ways, which makes sense. I should get the same answer. And again, what this really is asking, this when it says cosine of the angle between them, if the angle between them was 90, right? If the angle between them was 90, then I'd have cosine of that 90 and it'd be 0, and I'd get something that said I'd get a 0 dot product. If the angle between my two vectors was 90 here, one of these, they would completely cancel out on each other here, and I'd end up with vectors. One of these would be completely in the x direction, one would be completely in the y direction, say, and I'd end up with a 0. Or even if they weren't completely that way, they would cancel out, and I'd also end up with a 0 dot product. And that's why we say that these, when you dot I hat with I hat, you get 1. But if you do I hat, so again, if this is my x direction, so I hat with j hat, if you say this, you do a dot product with this, you'd say 1 is the magnitude times 1, but the angle between them would be 90. You'd say cosine of 90, and that would be 0. And so the dot products of unit vectors that are not the same unit vector are 0, and if they are the same unit vector, they're 1. So in number 35 that y'all do, number 35 that y'all do, you would use probably the magnitudes and angle and the directions, but in number 41, you probably would do that. Let's look at those really quickly, and we'll see what we mean by that. 35. Yes, and number 35 says two vectors R and S lie in the xy plane. Their magnitudes are 4.5 and 7.3 units respectively, and their directions are 320 degrees and 85 degrees respectively, as measured counterclockwise from the positive x-axis. So if we were going to try to draw that really quickly, so I'm not going to do this whole problem, but just looking at number 35, so sketching those two vectors, so my R vector is 4.5 units long, and it's 320 degrees measured counterclockwise from the positive x-axis. So this is positive x, so I'm going to say 320, that's all the way over here, right? 40 degrees below, and so here's my R vector. And then my S vector is only 85 degrees counterclockwise, so that's basically almost on the y-axis. There's my S vector. So the R vector is essentially here. If this is 320, then this is 40 degrees. Right? And so you've got the angle between them. The phi is going to be this angle, 85 plus 40. So for number 35, it's going to be easier to do this method to get your dot product, which is part A. For number 41, here they've given us our vectors in unit vector notation, our vectors in unit vector notation, and so it's going to be easier to do this other method for 41. Okay, I'm going to do the vector product in the last video, so I'm going to end this one here, and I'll do one more video on doing vector products.